Bismillahirrahmanirrahim. This is lecture number 18, process modeling simulation CHENG324. Today we are going to take problems to solve problems. So I will consider this as like a tutorial session. So today we will do a good job in solving problems. And to start with this, we need to open our textbook. And in opening our textbook, so these are the problems that we have here, and we are going to start solving problem 3.3, and this is like figure 3.3, and it says, and this looks like a custom of inputs. So we are starting something that we have explained just by the end of our lectures. And what it's asking us here is telling us that from the details calculate the pulse TW. Okay, so it wants us to calculate what is TW, and I think so that this is not like that kind of a question that we would really care about, but we need to understand that how does this response look like. Okay, so if you look at it, if we just look at it, and I'll try to, okay, I cannot take this thing in, so I think so we'll go to Internet Explorer, so it'll be easier to look at the problems. Okay, great, so that is the problems in Internet Explorer. So what do we have here? So we have, at 0 it started from a point up there, so it means that there was a step input here. There was a step input, and after that step input we had a ramp input, and after a ramp input, if I would guess, this is also went straight. That means there was another ramp at the opposite direction. Okay, so what do we have? We have step plus ramp plus well, this is like minus a ramp, I would say, and then plus a ramp, which made it straight. So these three things. So the step that it took up here, if this was H, okay, if I would say that was H, so I'm talking about a step of H over S, and then I'm talking about a ramp, and the ramp, if I would like to look at the slope, so it's H minus 0 over TW minus 0, so the slope is H minus 0 over TW minus 0. Okay, so that is like H over TW, and the H over TW, I'm going to write that directly, H over TW T, okay, because we call this as AT, okay, so it's minus slope into T, and then the same slope that goes to the other direction, which I would say that it will be plus H over TW T, okay. So this is what we have as an equation. Sorry, I mixed up here. Okay, the time, the S domain. So talking about only the time domain. So this is the time domain, and if I want just to put that in the S domain, that will be like H over S minus H over TW. Okay, so that is H. That is H over TW, and I'm talking about here 1 over S square plus H over TW, and I'm also talking about here 1 over S square. So that is the kind of a solution if we try to find. Okay, so this is what we have. Of course, if we have more information, we could also solve for it, and in this case, this is all what I need you to know in that question, is how to write this in terms of an inputs. Okay, so that was 3.3. That is what I need you to write. I need you to write in the time domain and then in the S domain. Okay, so let's go to question number 3.4. 3.4 says develop the Laplace transform of the input signals. So that is a custom of input. Again, I am having a custom of inputs by summarizing by summing component functions found in table 3.1. Okay, what is that table 3.1? Don't worry about it. We'll do the things that we can remember now. So at 0, it looks like that at 0 it started at 5, so there was a step input here, and this step input that I have, which started at 5, so it goes from 0 to 5. Okay, it goes from 0 to 5, so that is 5 over s. And then there was another step input that happened where it happened at okay, sorry, if I go to the previous one, I think I forgot something. I forgot to add the other slope term that happened at TW. So that was a big mistake. So that is here e to the power minus TWS. Okay, so I should remember that, because here I just remembered why, because I have 5 over s, and I just simply cannot say minus 5 over s. This will be 0. But the second step input happened where at 2. Okay, it happened at 2. So in this case, because it happened at 2, we would say that this is minus 5. But actually it did not go minus 5. It went from 5 to 1 only. So since it went from 5 to 1, so that will be like minus 4 over s. So it went only 4 units down. So minus 4 over s, that happened at 2 seconds. And then it went straight. What happened here? There was another shift down, which is minus 1 over s, that happened at 6 seconds. Okay, so that is my solution. That is my solution I would have here in the Laplace transform. So they derive the Laplace transform of the input signals. So this is the Laplace transform of the input signals. Okay, and what else do we have? We have question what we should solve here. I think so. This is good. Okay, I have part B. So what does part B tell me? I'm just thinking of going to part B or going to 3.5, because I hate when I look at TR and 2TR, 3TR, and it just makes it complicated for no reason sometimes, and it becomes all in the function of TR and 2TR and so on. I think so if I just remove this and say that like this is 1, this is 2, this is 3, I think it's better for your understanding. And here I will consider this as 3, for example. Okay, I'll consider this as 3. So if I have something like that, what will be the solution? So just to have more space here, so I'm going to go to my board. And my board, what do I have? I have something that looks like that. Okay, and we said that we have this, if I just can remember here. So this starts at 0 and 0. Okay, so that was an important information to know. So starts at 0 and 0. Okay, so this is 0, and just to make sure that I have the maximum. Okay, and that goes here at 1, and here at 2, and here it was at 3. We said here it's at 3. So what do we have here? What we have here is a slope. Okay, is a slope, and then we have another slope that cancel out that slope, which made it a straight line. And then we had a slope, and then we had another slope that made it a straight line. So if you can see here, we have a slope and then another cancelling slope at e to the power minus s, and that is just to make it bigger. So, and then we had a slope that was a minus slope. Okay, that was a minus slope, that one here. Okay, so you can see that one here, and then the one which cancelled it out, so that will be, so the minus slope happened at 2 seconds, and then the plus slope, and this is the slope 2, right? This is the other slope. The other slope, if I said 2, that would confuse you again. So this is the other slope. We're going to write the numbers now. It is the other slope, e to the power minus 3s. Okay, e to the power minus 3s. So simply what I'm trying to say here, I'm trying to say that this is equal to the slope, which is 3 over s, minus 3 over s e to the power of minus s, that happens at 1, and that remains till 2, where we have minus 3 over s, and you're going to see here like 2 minus 3 delta y, so delta y is 3 minus 0, and the delta x is delta y is 0 minus 3, and delta x is 3 minus 2, so it's minus 3 over 1. Okay, so minus 3 over s into e to the power minus 2s, and then the same slope that cancelled it out, plus 3 over s, that happened at 3 seconds. Okay, so that is the question that I had here for 3.4. Okay, so this is the solution of 3.4. Okay, so let's go to 3.5. The solutions are straightforward and easy, so I'm not really taking so much time in solving it. It should be straightforward. As I told you, we'll be solving like many problems. So let's go 3.5. The startup procedure for a batch reactor includes a heating step where the reactor temperature is gradually heated to the nominal operating temperature of temperature of 75 degrees. The desired temperature profile is shown in the figure 3.5. What is T in the S domain? Okay, so this is the response in the time domain. What we have is the response in the time domain, and what it is requesting us is to find out the T response in the S domain. Okay, so I think I have some space here, and I can do this. Can I do that? That's really much better, right? And I still can write. Okay, great. So talking about T in the time domain, this will be like a slope. Okay, it will be like a slope. But hold on. How did that start at 20? How did it start at 20? So it's either I say that there was, and I think so. I will say that there was a step input that took it to a 20 at 0, right? There was a step input that took it to 20. So that is 20 over s. This was very tricky. And then there was a slope from here till there. So I have a slope from here till here, and the slope is delta y, which is 75 minus 20. Okay, so I will say this is a positive slope. So it's 75 minus 20 over 30 minus 0. Okay, over 30 minus 0, and that is 1 over s squared because it is a slope. So here it will be 55 over 30, and minus the same slope, which is 55 over 30. That happens where? That happens now at e to the power minus 30 seconds. It happens here. Okay, so it happens here, e to the power minus 30 seconds. I have a slope which cancels out the first one. So that will be e to the power minus 30 seconds. That's nice. That's nice. And as it cancels out, khalas, it goes a straight line later. And so what we'll have, the answer is 20 over s plus 55 over 30 over s squared minus 55 over 30 over s squared into e to the power minus 30s. If you want to take common factor just to look at it in a different way, so this is 55 over s squared into 1 minus e to the power minus 30s. Okay, so that's the answer, and that is not in the T domain. Of course, we are talking about here the S domain, so that is like that. Okay, so that was 3.5. That was 3.5. I think that was a good question here. Going to 3.6, huge partial fraction were required. Okay, you know the story of partial fraction, right? And it is that only that I don't like to waste time a lot in finding the A, B, and C. So sorry for that, but I'll try to solve things, but I will not go through the details of A, B, and C. So if we have our first question, which is S, let me write that. So this is 3.6. So if I have S into S, okay, so that is S into S plus 1 over S squared plus, sorry, that's not S squared, into S plus 2 to S plus 2 into S plus 3 to S plus 4. It's getting slow. I don't know why the the laptop is getting a little slow here. It may need a restart. Okay, so s plus 2 into s plus 3 into s plus 4. So what should I do here? If you can remember, a over s plus 1 plus b over s plus, there's not s plus 1, there's s plus 2, plus b over s plus 3 plus c over s plus 4. Okay, so this is what I have here. So this is what I have, and looking at it, it looks great actually. And what I have here is just finding out now the solution, and if we just multiply both sides with the with the denominator, so this will cancel the denominator, so it will be s into s plus 1 is equal to a into what, why I, yes, that's right, now it's correct, sorry. So that is a into s plus 3 into s plus 4, b into s plus 2 into s plus 4, and that is plus c into s plus 2 into s plus 3. Okay, and how to solve that? We are going to take different values of s. So considering that, for example, s is equal to minus 2. So when I say minus 2, I'm going to have terms that are going to be cancelled out. So this one has a minus 2, so it will cancel out. This one has a minus 2, it will cancel out. All those terms, so this will be 0, 0. So the answer here will be minus 2 plus 3, which is plus 1 into 2. Okay, so 2a is equal to 2a is equal to 2, if I think so. Yeah, 2a is equal to 2, so that will be a is equal to 1. And then similarly, of course, if you substitute s to be equal to minus 3 to find the value of b, you're going to find that the value of b is equal to minus 6, and if you substitute minus 4, you're going to find the value of c, okay, to be 6. And by that you're finding the solution, and the solution here in this case, after finding the values, x of s is equal to 1 over s plus 2 minus 6 over s plus 3 plus 6 over s plus 4. Okay, so we found the terms, and if you want to now find x of t as requested, so x of t, this will be e to the power minus 2t multiplied by this one here, minus 6 e to the power minus 3t plus 6 e to the power minus 4t. And as you can see here, that all exponential terms are negative, because we have the poles are negative. So if you say set s plus 2 is equal to 0, so s is minus 2, here s is minus 3, s is minus 4. So the values of the poles tells me that if the poles are negative, all poles are negative, it means that it is a stable process. And why is it a stable process? Because all of the exponential terms will be decaying, Okay, great. So that was a good problem that we had tried to solve here in our problem. Great. Okay, so I'll just go out of this and I'll open a new whiteboard and let me check. Okay, so that's my new whiteboard, and I think so now, yeah, now it's much better. It's much better now. Okay, great. So going back to our problem here, we already solved 3.6, the first part. Very similarly, if you want to solve the other parts, actually it's not similar, because the second one is a little different here. We solved something similar to that, but we just need to consider, if you sometimes look at the book, how did it solve the second part? It solves with a different way from the way how I solve it. Okay, so it separates this into two conjugates and deals with the conjugate like s plus 2j into s minus 2j. I don't do this. I look at that, I know that there's a complex root, and because there's a complex root, I do shape it into a way that I can do the Laplace inverse for it. Okay, so I totally do it in a different way. So if I would present this in a problem, in this problem, what I would say s plus 1. So I think I need to make this a little smaller. Okay, so if I would say that if I have s plus 1, sorry, so s plus 1, and the question is over s plus 2. So again, I'm writing the problem. I just restarted my whiteboard so that I can write faster. It was a bit slow. So x of x is equal to s plus 1. Yeah, that's much better. Into s plus 2 into s plus 3 into s squared plus 4. Okay, so that is my problem here. So now if I want to work on this, so this will be like a over s plus 2 plus b over s plus 3 plus, since I have s squared plus 4 here, I'm going to have at the top here cs plus d. Okay, so it's one order less. I know that the answer, I already know that the answer from this part, I know that the answer from this part is going to be what? It's going to be an exponential term. It will be a. Okay, so I just need to have a smaller one, please. Yep. So that is a e to the power minus 2t, and that will be like b plus b e to the power minus 3t. And the last part will be, it will be both a sine and a cosine term. And if you look at s squared plus 4, if you remember, what should we do? If you remember what we should do, we just take the square root of that and take the square. So it's exactly the same. So it's, I'm saying square root of 4 square. Okay, and in that, which means that I have square root of omega square. So what is my omega? Omega is square root of 4. And this is the way that how we deal with it. And since we have square root of 4, so definitely my answer is going to have square root of 4 is 2. So just to make it easier, so I'm going to have here a certain term, and then I'm going to have a sine 2t, and plus another term, this like I would say like c and d, and that will be cosine 2t. Okay, so it's like so this is my answer, right? I already can see how my answer would look like, what my answer would look like, and what I need to do is to try to solve this problem, is to try to find the values of a, b, if we find the values of a, b, c, and d. Okay, so this is what I'm going to do here. I'm going to leave the math to you so that you can work on it. Okay, so what do we have here? Okay, we were on Internet Explorer. That's our Internet Explorer. Okay, so if you go to the third part is going to be like a over s plus 1 or plus b over s plus 1, the whole thing squared. So that is the part D, part C. Part D, we have 1 over s squared plus s plus 1, and here first thing I'm going to ask, is this it has a complex root or not? If it has a complex root, I need to reshape it as a complex root. If it doesn't have a complex root, that means I need to factorize it, right? And factorizing will be then straightforward. So if I go to D, I think so it's a good idea to solve for D. So what do I have here? So that is my place. Okay, so okay, that's good. So what do I have here? I have the problem says that if I have, this is part D. Okay, so if I have x of x is equal to, I'll write that in white. X of s is equal to 1 over s squared plus s plus 1. Okay, and if you just want to check if we have complex roots, so that is minus b, which is, I don't care really about minus b and all this thing. I care what is under the root. So b squared minus 4ac here, b squared is 1 squared minus 4ac, which is minus 4. So definitely I can see here that I have a negative root, and having a negative root, having a negative like that, which means that I'm going to have a complex root, and having a complex root, that means I need to reshape this. I need to reshape it, so I have something that looks like something that I need to convert, Laplace invert to the time domain. So if I can remember, if I have something like that, if I have anything that looks like that means I need to get a shape that looks like that. Since I have only a 1 without an s at the top there, so I'm going to have a shape that looks like that. Omega plus s plus omega square plus omega square. So and that will be, and that the answer will be of that is e to the power minus at into sine omega t. Okay, so I'm trying to get the answer of that. So I'm trying to get the omega value and the a value, which are here, right? So what do I have here? First thing, I need to complete the square. So I need to complete the square of this part here. How to complete the square of this? So if we just can recall, s squared plus s, and then we take half of that s here, which and half of it means I take 1 is the number, over 2, so I divide it by 2. That's why I said half of it, and that is square. So we add that number, so I can have s plus 1 the whole thing square. Okay, so we add that number, so I can have s plus 1 the whole thing square, and I subtract that number as well. Okay, I do subtract that number as well. It's like adding 0, and that is plus 1. That is plus 1. So what do I have here? If I continue, I will have something like s plus 1, the whole thing square. And what else I do have? I just have the term which tells me plus 1 minus half square. And plus 1 minus half square, I just need to calculate this. So what is plus 1 minus half square? Half square is 1 over 4, so definitely this will be 0.75. And since I have now 0.75 at the bottom there, so my solution now is easy, and I have omega, and my omega term, I just need to multiply by my omega, so I have the omega term at the top. Hold a bit. Okay, I need to be careful here. So this is omega square. What I have here actually is omega square. And since I have omega square, all what I need to do is that, you just look at it, right? Square. What did I do? I did nothing. I simply did nothing. I took the square root and then I did the square. Just to say that my omega was 0.75 under the square root. So I'm going to multiply here by 0.75 under the square root, and definitely I'm going to divide by 0.75 under the square root. So what do I have here? I'm having my term will be 1 over omega 0.75, and now I have my complete term, which looks like that: 0.75 over s plus a, the whole thing square, plus the omega that I have square. And if you can see this number, this is 0.75, right? As we obtained earlier, here 0.75, so this is 0.75. And now when you do your Laplace inversion, you're going to get a value of the following, which is 1 over square root of 0.75, and this is e to the power minus at, which is e to the power minus 1t, into sine omega here is 0.75t. Okay, so that is the solution of this part here, and actually it was a very good practice. The last part, what I want to deal with here is e. E is equal to s plus 1 over s into s plus 2 into s plus 3 e to the power minus 0.5s. Okay, so he wants us to do the partial fraction. The thing that I just want to mention, that e to the power minus 0.5s will remain by itself as e to the power minus 0.5s. So we will not do anything with that. There is something that you can do, of course. It's not that I'm not saying that you cannot do anything with it, because we can deal with e to the power minus 0.5s with something called the Paddy approximation. But we did not take that yet, so we will say that simply for this problem, for this part, is going to be kept as it is, e to the power minus 0.5s. Okay, so we are going to ignore the time delay, and we are going to work only on the other parts. And the other parts, they're straightforward. A over S plus B, B over S plus 2 plus C over S plus 3. We find A, B, and C. We substitute them, and at the end of all our story, after we finish, we just can include our term here of the delay. Okay, so I'm not going to solve that. It looks like straightforward. Okay, so what do we have here? We have 3.7, and 3.7 says, let me see if I want to solve 3.7. Expand each of the following functions into partial fractions. Again, the same story. So we will not solve 3.7. And for that means I'm going to go to let me see, 3.10. Okay, 3.10 looks good. Okay, so we'll try to solve 3.10. Okay, so 3.10 says that if I have a group of systems, and this group of systems, I don't know if they exhibit some kind of oscillatory process or not. So it tells me that for each of the following cases, determine what functions of time example constant e to the power minus whatever t will appear in y of t. Not what that you do not have to find y of t. It doesn't want us to find it. Which y of t are oscillatory, which exhibit a constant value of y of t for large values of t. Well, let us make it simpler. So I want to know that if it is oscillatory, and I want to know that if it is stable or not. Okay, so these are, oops, okay. So these are the two parts of my question. Okay, these two parts of the question. Is it oscillatory? Is it stable? So going to the first part, y of s is equal to 2 over s square, s into s square plus 4s. To know that if it's oscillatory or stable, we just need to look at the denominator. Okay, oscillatory, that means in the denominator I have complex roots. Stable means that all poles are negative. Okay, all the ones at the roots of the denominator. Poles means the roots of the denominator. Okay, so I always say that, but it's good to remember. So poles are roots of the denominator. So simply, what I'll try to do in this question is to find the roots of the denominator, and then I find if they are complex and they have real parts which are negative. So in this problem, it's very clear that I have so I have s into s squared plus 4s is equal to 0. So I have s is equal to 0, and the other one s squared plus 4s, which is if I take a common factor of s, so that will be like s into s plus 4 is equal to 0. So s is equal to 0 and s is equal to minus 4. And since I have in my problem that I have a 0 term here, and if we have s is equal to 0, that is exactly like having what they call it an integrating process. So in this case, I would decide in 3.10. I would decide in 3.10 that it's not going to be stable, and it's not going to be stable. I can find the solution, by the way. I can find the solution if I would like, but it's very clear that it will not be stable. Okay, it will not be stable if t approaches infinity. Is it oscillatory? No, it is not oscillatory because we have no complex roots here. Okay, so this is one way of looking at it. Okay, so this is the one way of looking at it. Someone else would do something else. Someone else would say that, well, if I have y of s, let me do that in the whiteboard. So if I have if I have in this 3.10 in 3.10 2 over s into s squared plus 4s. So instead of finding only the roots, what I'm going to do, I'm going to say that this is something like, over partial decomposition is a over s plus, this is like s into s plus 4s, right? So if you just look at it, this is like s into s plus 4s. Let me do that first, so that I think you will get confused. So this is like s into s plus 4s. So it will be like 2 over s squared, right, into s plus 4s. And now by looking at that, how to do this partial decomposition is a over s plus b over s squared plus c over s plus 4. Okay, plus c over s plus 4. So it's s plus 4 here. And the solution of that, after you do your Laplace inverse part, after you do your Laplace inverse, this will be like a plus bt plus c e to the power minus 4t. And as I said, it looks like we have a component that will decay, but we do have another component because of this integrator, and I can see the integrator here. As we already have seen that we had one of the poles is equal to 0, which shows that it is like an integration process, and I can see that it's an integrator process, and the integrator process in the t domain is t. Okay, so this is the way how we can see how to solve 3.10, the first part of 3.10. So let's go to the second part. The second part says 2 over s into s squared. Okay, so I'm going to write that here directly. So 3.11, and that is hold a minute. Yep. So that is y of s is equal to 2 over s into s squared plus 4s plus 3. Okay, so that is the question that we have here. So we said that it's easier to look at the poles, but if you want to do it on partial decomposition, so that is a over s. And let me see if this can be factorized before I start directly doing this. So I think it can be factorized. Let me look at that. Yes, it can be factorized. So this s into s plus 1 to s plus 3. Definitely it looks like something that can be factorized here easily. So it will be a over s plus b over s plus 1 plus c over s plus 3. Okay, so that is my part here. And that will be, if you can see here, the answer will be here a over s. The answer will be like a plus b e to the power minus t plus c e to the power minus 3t. And in this case, it looks like it is stable. It will be stable, even though that when finding the poles, we are having one of them is equal to 0, one of them is equal to minus 1, and one of them is minus 3. And actually this s is equal to 0. It worries me a lot that this system could be unstable, or through knowledge that this is unstable. Okay, this will be unstable just because of that s that I have here. And we will hold on here because I think so that if we have two s's at equal to 0, this is the problem that we'll have. But if you have one s is equal to 0, I don't think so it's a problem. So I'll just take out that. Okay, so in this case, our things are normal and we don't have a problem and we don't have an integrating process. Okay, so that is a solution of two different ways. If you go to part 3, y of s is equal to 2 over s into s squared plus 4s plus 3. And this after factorizing will be something like s into s plus 1 to s plus 3. And again, the same story I'm going to have here. Well, I have a over s over b over s plus 1 plus c over s plus 3. And this will be, after taking the Laplace inverse, it will be a plus b to the power e minus t, c to the power minus 3t. So things are going to be stable. Is this the same problem? I think so. I took the same problem and I solved it again. Actually, the next problem was s plus, that is plus 4, and that was what it confused me with. Okay, so it was 2 over s into s squared plus 4s. So it's exactly the same question. Instead of placing plus 3, it was plus 4. And since it is plus 4, it is going to be something like that after factorization. And if doing this will be 2 over, this will be like a over s plus b over s plus 2 plus c over s plus 2, the whole thing square. And the answer of this will be like a plus b e to the power minus 2t. And here we are going to have like ct. So we have a t term, and then I'm going to have e to the power minus 2t. Okay, so there is like something between, this is growing, the t, but this is also decaying, putting down the effect of that t. Okay, so there's a challenge here of how to decide if this is stable or not stable. But definitely all of our problems are not oscillatory. All of our problems are not oscillatory, and actually this was what asked by the question. And the last part here, the last part in which I have my system is going to be 2 over s into s squared plus 4s plus 8. And as I always say, that if you look just at the poles, you know that if it is oscillatory or not. And again, if you just look at the poles here, if you just take under the square root minus b squared minus 4ac and check if you have complex roots, and you'll find out that you will have b squared, which is 16, minus 4ac minus 32. So you will have a negative term here. So definitely you will have complex roots, and since you will have complex roots, you will have a sine or cosine or both. Okay, so you will have that, and you need to fix this to be appearing to something that looks like a sine and a cosine. If you want to do this like just quickly, so that will be like s squared plus 4s, and this 4s, if you remember, we take half of it, so it's 4 over 2, the whole thing square. Okay, so to be like that, 4 over 2, the whole thing square, and we subtract minus 4 over 2, the whole thing square, and then we have plus 8. So we were adding these two terms, and by adding these two terms, we will have s plus 2, the whole thing square. So this will be like that, so it will be s plus 2, the whole thing square, plus here I have 8 minus 2 square, which is 4. So I have here 4. So I would say that would be 2 square. Okay, and I think so I already have a 2. So it is made ready for us. So I already have my system here very clear. So if I want to write that like a over s plus b over the second term, which is s plus 2, the whole thing square, plus 2 square, and then I just can multiply by 2, divide by 2. If you find a and b, you're going to find that you will have things being fixed. Okay, so we already now know the solution, so we don't need to go through the last part here. Okay, so what else do we have? So again, it's asking us here if these are oscillatory or not, but this needs a computer kind of thing. But you can take Laplace, and after you can take Laplace from the poles, you can know that it's oscillatory or not. So we are not going to go to 3.11, but this is the way. You just take the Laplace and then find the poles. Okay, I think you know this, right? So I don't need to go through it. So what else do we have as a problem? So we have a problem like 316. Let's solve 316. Okay, it just came to my mind, why not to solve 316? So I just want to write our problem here. Okay, so 3.16, and our problem says that d square y by dt plus 6 dy by dt, and that is plus 9y is equal to cosine t. So that is my system. And the initial conditions, oh, they are not 0. Come on, because they are not talking about deviation formats, right? If they are not talking about deviation formats, they will not be 0, okay? Because you're not subtracting it by the initial condition, the initial state. So this is x prime of 0 is equal to 2. Find y of s without finding y of t, okay? So it just wants to find y of s. So if you just do the Laplace thing here, so what I'm going to do, I'm going to take Laplace. And by taking Laplace, okay, by taking Laplace, this will be x squared y of s. Did they say x? X? Let me see that just in a moment. Okay, here's giving us the initial condition for x. Actually, it should tell us the initial condition for y. Okay, so at y at 0, y at x is equal to 0 is equal to 1. So this is by mistake written by the problem here. So these are y's. Okay, these are y that we have here. And if you go to the solution, so this is s squared y of s minus s y prime minus s y prime 0 minus y double prime 0. Okay, I don't have y double prime 0 here, so I think so we are getting some kind of a challenge problem here. Okay, I did some mistake here. So this is minus sy of 0, and then it becomes minus y prime of 0. Okay, so that is the first part, and then plus 6 dy by dt. I'm going to continue that, so plus 6 dy by dt. So this is s y of s. I would write it here, so I have my y s's under each other. So this is like plus 6 s y of s. Oh, okay, it is s. Yeah, that's right. Plus 6 s y of s and minus y 0, and the last part is plus 9 y of s, and this is equal to cosine t. And if you go to cosine t is like s over s squared plus 1. So that is cosine t. You're going to find that in the tables. So doing some kind of rearrangement by taking y of s as a common factor and taking y of s as a common factor and rearranging it, you're going to find the final shape of your problem is equal to something that looks like that: s cubed plus 8s squared plus 2s plus 8, okay, plus 2s plus 8 divided by s plus 3, the whole thing square, multiplied by s squared plus 1. Okay, so that is my my solution, and of course I can find y of t here. And if I look at that, this is s squared into s squared, it's s to the power 4, so it's one order above the first one, so that will not be a problem, and we don't need any long division to find the solution of that problem. Okay, great. So all of chapter 3 is about solving Laplace. So all what we have trying to do here in this problem is solving Laplace, as simple as that. Okay, so you are trying to solve Laplace. Okay, great. So that's page 94. Okay, and I think so that just looking at the problems that we have here, I think we solved most of the problems that you need to know how to deal with Laplace. So I can conclude the part of chapter 3. I can conclude the solving of chapter 3. So next time we are going to see you solving the parts for chapter 4. Okay, so see you next time to solve chapter 4. All the best.